We're going to look at a different rule or technique for integrating today. Let's review the really helpful technique that we learned earlier, though. So if we have the integral 2x times the square root of the quantity x squared plus 1 dx, I think that should be very obvious to you at this point that you're going to use a u substitution of u as x squared plus 1. And if you do that, sparing you all the details because that's not the emphasis here, you're going to get 2/3 times the quantity x squared plus 1 to the 3/2. And since it's an indefinite integral, plus c. Now, the reason why I want to start here is just to review u substitution, but also to show you the kind of function you're going to get when you do u substitution like this. Notice that we got a composite function. We got a function, something to 3/2, of another function, x squared plus 1. So when you do a u substitution, you oftentimes get a composite function as your resulting antiderivative here. Well, what if when we have the integrand, there is no obvious u substitution for us to use? So before we do that, let's go ahead and review a little bit. We're going to go back and go to the product rule. Now, I think some of you guys are thinking, hold on a second. I thought we were doing integrals here. The product rule is for derivatives. It is, you're right, but also that you learned is derivatives and antiderivatives are just inverses of each other. So it would serve to reason that a rule that I have for differentiation could possibly, very likely, have a similar rule for antidifferentiation. So suppose I've got the function uv, right, and I want to differentiate that with respect to x. So u and v are both functions of x. So I'll do d dx of uv, and that's going to be, the way that I like to write this out, is the second v times the derivative of the first du dx plus the first u times the derivative of the second dv dx. Now remember, I write that out so that way the order here of the differentiation for the product rule is the same as it is for the quotient rule. So all you have to remember early on is whether you flip the positive or the negative sign for the two rules. So that's why I like to do that, just remember here. I can multiply everything through by the differential with x, if you will. So I have d of uv equals v du plus u dv. All right, so what do I want to do? I'm going to manipulate this. Don't really worry about y at this point, but I'm going to solve this equation for u dv. So I'll say u dv, so some function times the differential of the other function is going to equal d of uv plus, oops, that would be a minus v du. Right, so we've got that. But what if I wanted to integrate this, right? Because we're looking at integrals now. So I can integrate both sides. So I'm going to integrate u dv, and that's going to equal the integral. Now pay attention to the differential here. This is the differential of uv, not just u and not just v, but the differential of the product of uv, minus the integral of v du. Well, there's nothing I can do to simplify because the variable of integration, v, is not the same as the variable in my integrand. So that just remains the integral of u dv. I can, however, simplify this because my constant, if you will, here is 1 times this differential. So if I'm integrating 1 with that differential, it is just whatever the differential is, minus, and I can't simplify that because my variable of integration is u, the variable of the integrand is v, so it's minus v du. This is called integration by parts. This is the technique that we're going to be using here. So suppose I've got some function here, or some integral of function, and I've got another differential. It's not of the same function. And then I want to be able to find the integral of that. Well, if I know what u and v are, then it's going to be u v minus this integral v du. You set up this integral, integration by parts, such that this integral of v du is going to be easier to do than the integral of u dv. All it is it's the product rule backwards. That's really all it is. Usually what we have here, and this would be key for you to write down, usually you're going to choose u so that it'll eventually differentiate to 0. Not always, but you want to set that up so it's going to, if you have to take successive derivatives of u, you can keep doing that and it'll eventually approach 0. Not always, but usually. And then for dv, you usually want to choose that such that it's going to be something that's easy to integrate. So it just takes some practice. So how do you choose what to use for u and what to use for v? So this is key. This is a guideline. It's not always the case, but it's a really good guideline to choose or to look at. So you're going to choose u generally, I want to emphasize generally, not always, but generally, in this order. All right? And then the order is going to be the reverse order of ease of anti-differentiating. So why do we do that? The reason why we do that is because u is what we differentiate and dv is what we anti-differentiate. So we want to choose u to be the most difficult thing to anti-differentiate first, the most difficult type of function to anti-differentiate. And here you go. I think many of you, if you stop and think about it, would agree with this order of anti-differentiating. So it's called, a nice mnemonic here, LIPET. Again, this is just a guideline. It works most of the time, but not always. So L is going to stand for logs. So if you have any logarithms in your problem, you want that to be u. Right? You want to set that to be u. The next one that you would set u to, if there aren't any logarithms, I stands for inverse trig. So if you have arc sine or inverse sine, same thing, trig function in your integral and you don't have a logarithm, you want to let u be the inverse trig. P is your polynomial. Those are relatively easy to anti-differentiate. Definitely easier than the other ones. E, something that's really easy to anti-differentiate would be exponentials, at least if it's e to the x. And something that's very easy to anti-differentiate just because you have to memorize them are trig functions. So if you see any of these functions here in your integrand, you want to let u be logs first. If there are no logs, then let u be the inverse trig. If there are no inverse trig functions, let u be polynomials, etc. Say you have a polynomial and a trig function, you let u be the polynomial. You let u be the polynomial. Trig functions, super easy to anti-differentiate, like I said, because all you need to know are the definitions of them from before and what they are. All right, so let's practice here. Let's get some examples, because that's the only way you're going to be able to really handle this stuff. So suppose we've got the integral of x times cosine of x dx. So up until today, what you would do is you would try to say, okay, I want to let u be x or cosine of x, and then you do a u substitution, find du, and that would work out all fine and dandy. But it doesn't in this case. So when it doesn't work out very well, we have to use integration by parts and hope that works. So what we have here is we've got a polynomial, and we've got a trig function. So we can let u equal x or u equal cosine of x. Well, according to LIPET, and I'll just write that up here so we've got that. X is a polynomial, cosine of x is a trig function. So we're going to try letting u be the polynomial, or so x in this case. All right. So we have u equals x, and then we want to find du because that shows up in our equation. I guess the other thing I'll put over here is the integral of u dv equals uv minus the integral of v du. Okay, so very important box up here. So we're finding the integral of u dv. So if we let u be x, you can see the answer involves a du, so that's why I have to find du. Well, then dv is going to be your differential. It's going to be everything else in that integrand. So we have cosine of x dx. Cosine of x dx. So that's dv. Now you can see over here, to solve for this integral, we need v. So I have to anti-differentiate cosine of x dx. Usually it's going to be something that's relatively easy to anti-differentiate, which is sine of x. We don't have to worry about the plus c here, but if you're thinking about that, good for you. Now, what do? Oh, we've got the integral of x cosine of x dx, and this equals, now keep in mind, this is all a result of integrating the product rule, that's all. So it's u times v, x times sine of x, minus the integral of v times du. Make that look more like a v there. So v is sine of x, and du in this case is just dx. Well, we're not out of the woods yet. Just because I wrote some expression down here on the right-hand side doesn't mean that I'm done. I can certainly perform this anti-differentiation. So we've got the integral x cosine of x dx equals, we have this expression, x sine of x. Now we can anti-differentiate sine of x. The antiderivative of sine of x is negative cosine of x. So minus negative cosine of x is plus cosine of x. Now, since we're doing an indefinite integral, we need the plus c. So something that we weren't able to differentiate before today, we're now able to differentiate. And of course, what you should and could always do, especially when you're first learning something, take this and differentiate it. Take this answer and differentiate it. You will get x cosine of x if you do it correctly. Keep in mind, we've got a product rule here for x sine of x. It should not surprise you that we have a product rule, because that's where this comes from. All right, let's take a look at some more examples. What if I want to do the integral of the natural log of x dx? Up until this point, I just had to give you the rule. I just gave you the rule for what the integral of natural log of x was, and I said it was x natural log of x minus x plus c. And you just listened to me and said, okay, that's fine, we'll take your word for it. Well, the reason why I gave it to you is because you didn't have the skills yet. Now we're able to do this. We've got here natural log of x, and then we've got just dx, or really, if you want, 1 times dx. 1 being a polynomial, a very uninteresting polynomial, but polynomial nonetheless. Keep in mind Lipit and the integration by parts equation here. Okay, the integral of u dv equals uv minus the integral of v du. So I'm writing this down every single time. I think it's definitely worth your while to write it down a few times as well. Anyway, so we've got two functions. It doesn't look like it, but we do. We've got the natural log of x as one function, and like I said, times 1 dx, 1 being a polynomial. So we have a natural log, and we've got a polynomial. Well, according to Lipit, what our guide is, the log will be u. So we'll let u equal the natural log. We'll let u equal the natural log of x. Now, of course, the derivative of the natural log of x is just 1 over x dx. Remember that differential there. And then dv just equals 1 dx or dx. If it helps you to write the 1 there to do the anti-derivative there, great. So anti-differentiating dv, I'm going to get v. Anti-differentiating dx, I'm going to get x. So we've got the integral of the natural log of x dx. All right, so this is u times dv. Now, it's not always in that order. I just want to caution you. It's not always the first function written down is your u. The second function written down is your dv. So just be careful about that. That's why I gave you the mnemonic Lipit to help you reason through that. I don't want you to always think from these first couple examples that the first function is u. Not the case at all. So we have u times v. So we have natural log of x times x. We want the parentheses there to make sure that we know that's not both x's in the argument for the natural log, minus the integral of v du. So x times 1 over x dx. Well, just breaking that down, we got the natural log of x dx equals the natural log of x. Usually we'll put the x out front. We like to write logarithms last. Let's just do a little quick mental math here. X times 1 over x is 1. So the integral of 1 is x, so it's minus x. Since it's an indefinite integral, plus c. So again, using the integration by parts method there. All right, let's continue on with some examples. So now suppose you have the integral of e to the x times x squared dx. Now, this might look like a great u substitution problem to you on the surface, but it's really not, because if you let u equal x squared, you're going to get this e to the x. If it was e to the x squared times x dx, that's a u substitution problem. You should do that. So just up in this corner, I'm reminding you of Lipit and the integration by parts formula here. I'm not going to do this every single time, but again, it's new. You're going to want to practice it. Write it down in general every single time before you start a problem. So we have e to the x, an exponential, and we have x squared, a polynomial. Well, Lipit says, let u be the polynomial. So let's try that. So u equals x squared. You can see, like I was saying, it's not always the first function written, so we've got to be careful. Du equals 2x. dv then is what's remaining, e to the x times dx. Well, here's the reason why we follow Lipit, because e to the x is very easy to anti-differentiate. It's just e to the x. All right, so what do we have? We have the integral of e to the x times x squared dx equals u times v, x squared times e to the x, minus the integral of v, e to the x, times du, forgot my dx up there, 2x dx. All right, so we look here, and now to integrate this, shoot. What we need here is another integration by parts. Sometimes you need more than one. Just like when we were doing u substitution, sometimes we needed more substitutions than just a u substitution. Technically, what I should do here is anything other than a u and a v, but just to help you out, we'll do this. So we'll say u equals 2x, du equals 2 dx, and then dv equals e to the x dx. So v equals e to the x. All right, so continue on. We have e to the x, the integral of e to the x times x squared dx equals, we'll keep this x squared minus, or x squared times e to the x, minus, don't forget your parentheses there, minus u times v, because we're integrating this by parts, which is 2x times e to the x, minus the integral of v du, which is 2e to the x dx. Finally, I got an integral that I can do. That's just 2e to the x. So we have the integral of e to the x times x squared dx equals x squared times e to the x minus 2x e to the x, distributing that negative through, and then minus a negative, so plus the integral of this just happens to also be 2e to the x, plus c, right? Remember that plus c. So there's another way that you can look at this problem. I'll do it on the same page because it's the same problem. When you see that you're going to have an integral that you're not going to be able to do again, like x squared, that goes to 2x, and then that's going to give you another function. You can set up what's called the tabular form here. The tabular form is kind of a shortcut, not kind of, it is a shortcut to doing multiple integration by parts. So the tabular form. So what we'll do here is we're going to choose f of x for u, right? We'll say u equals f of x, and then that's x squared in this case. And then we'll say g of x equals e to the x. Okay. That's going to be v, right? It's the integral of your dv. All right, so when would you use the tabular form? You're going to use this method when you see that you've got your function, your dv piece that you choose, that's going to have some sort of repetition for the antiderivative. So here we're going to differentiate for the u column because that's what we do. We're going to differentiate. All right. And then here for the v column, we're going to anti-differentiate. We're going to anti-differentiate. Our mouse is going crazy today. All right, we're going to anti-differentiate. So, all right, let's see what we have here. So we have x squared. U, we'll differentiate that. 2x. We'll differentiate that. 2. We'll differentiate that. We get 0. Once we get to 0, we stop. Just like I said before, a lot of times, if we can, we'll choose u such that it'll differentiate to 0, not always. All right, and then now we have e to the x. We're going to anti-differentiate e to the x. Happens to be e to the x. We're going to anti-differentiate e to the x. We're going to get e to the x. We're going to anti-differentiate that. We're going to get e to the x. These are not always the same, but oftentimes they are. So this is your u, that's your v. So that's uv. And what we're going to do, that'll be positive. And then what we do, this is your du, and this is your second v. We're going to subtract those. And then we're going to add those. So we alternate addition and subtraction here. Like I said, it's just a shortcut. But if you look here, we get x squared times e to the x, negative 2x e to the x right there, and positive 2e to the x. So you're going to use the tabular form when you've got antiderivatives that just kind of repeat. Think exponentials, think trig functions. Those are good places to use the tabular form. Let's look at one more example. I know it's getting a little long here, but a lot of different examples you want to see for anti-differentiation by parts. This will be the final example. So suppose you've got the integral of e to the x cosine of x dx. So suppose we have something like this. Now it might look like, hey, we want to use the tabular form because we can see one or those are going to repeat, but one of them isn't going to 0, so we'll just keep spinning our wheels and going all day. So tabular form, not a good thing. Using Lipit, exponential before trig. So u equals e to the x, du equals e to the x dx. Well, that's easy enough. And then we'll say dv equals cosine of x dx, and v equals sine of x dx. Oops, not dx, just sine of x. Cosine of x there. All right, so here's where if you've been listening to me all year saying, let's be very careful about what we have. Let's always start with our expression and set that equal to something. If you weren't listening to me about that throughout the year, you're really going to want to do that here, because if you forget this step, what we're doing is going to make no sense to you, and you will continue on forever. This is going to be an infinite integration by parts problem, unless you follow my advice. So it's uv, e to the x, times v, so sine of x, minus v du, or the integral of v du, which is going to be sine of x, e to the x dx. But that looks like an integral that we don't know how to do. So we're going to need another u substitution here. So we'll let u equal, again, the exponential, e to the x, du equals e to the x dx. We'll say dv equals sine of x dx, and then v equals negative cosine of x. All right, so continuing on. Remember to write out that initial integral on the left-hand side. I cannot stress that enough for a problem like this. You miss it here, like I said, you will be doing this forever. And that's something we don't want to do. So it's going to be e to the x sine of x minus u times v, which is negative e to the x cosine of x, putting the exponential first, just because that's typically how we'll do, minus the integral of e to the x, e to the x negative cosine of x. So minus e to the x cosine of x dx. So we've got that, right? The negatives from there. Now I'm going to simplify this a little bit just before I go any further. So the integral of e to the x cosine of x dx equals e to the x sine of x minus a negative, so it's going to be plus e to the x cosine of x. This is minus a negative integral, so that's going to be positive, but minus that positive, lots of negatives, minus the integral of e to the x cosine of x dx. So if you've been following my advice about writing that original integral down, you're going to see, wait a second, this looks really familiar. The integral of e to the x cosine of x dx. That's what I'm trying to find out. So if you don't recognize that because you haven't seen that and you haven't been writing that out a lot, you're just going to keep doing u substitution and integration by parts for a long time. You're just going to keep doing that until you're done. But we can actually be kind of clever about this. We have this integral of e to the x cosine of x dx and this integral of e to the x cosine of x dx. What I'm going to do is I'm going to add the integral of e to the x cosine of x dx to both sides. So it's going to be 2 times the integral of e to the x cosine of x dx equals e to the x sine of x plus e to the x cosine of x. remember that we took this integral and we added it to both sides. Well, what I'm trying to do is I'm trying to solve for this, right? I have 2 times that integral, so I just simply divide both sides by 2. So I've got the integral of e to the x cosine of x dx equals that sum, e to the x sine of x plus e to the x cosine of x, all divided by 2. And since it's an indefinite integral, don't forget your plus c. So I know there was a lot of stuff in this presentation here, but let's keep that in mind in terms of what we're doing. We're using a new technique. It's the integral technique of the product rule that we're using. So to choose your functions, follow that mnemonic of Lipet, and then really be careful about what you're choosing for u and v according to that. And then remember that general equation for integration by parts. Integral of u dv equals uv minus integral of v du. The more you practice it, the more you write it down, the better you're going to get it. So that'll be the section for integration by parts.